Okay, this is another example of drawing the shear moment diagram for a beam when the loading is variable, and we may use the equations for shear and moment in determining the important data along the span of the beam, that the relationship between load, shear, and moment diagram may be more complicated than using the shear and moment equations. So we will have an example. The span of the beam is 8 meters, and the loading is varying from maximum at 20 sport a magnitude of 42 kilonewtons per meter to 0 at 20. Okay, we'll just reserve the space for diagrams. The solution will start again by determining first the reactions. We have to solve first the reactions before we can determine the different values of shear moment along the span of the beam. Some moment at point A equal to 0. You have counterclockwise positive. Plus will be times 8 meters. Then minus total force due to this regular loading will be acting at 1/3 of the span from point A. And the area is 1/2 times 42 times 8 meters. And then the moment arm is 8 meters divided by 3. Equal to 0. And then R sub B. Of course, should be apart. And then moment summation at joint B equal to 0 clockwise positive R sub A times 8 meters minus the moment arm from point B of this force will be 2/3 of the span, but the area is 1/2 42 times 8 meters times 2/3 of 8 meters and 0. So to check the reactions, R sub A plus R sub B, will it be equal to 1/2 times 42 kilonewtons per meter times 8. Yeah, 56 plus 112. Is this equal to 168? 112 plus 56 is 168. So it's okay. There is playroom along the vertical direction of the forces. The sum of the reactions just equal to the total applied load. So now we'll solve for the magnitude of the shear from point A to point B. This is our shear diagram. This will be our moment diagram. The shear diagram will have values. We'll compute first the shear values. At point A, again, we will have to imagine a point where R sub A is acting at the center. This point starts with 0. B sub A 1, a little to the left of point A is 0. And then at the center of point 1 is R sub A. And B sub A 2 is B sub A 1 plus R sub A. And this is 0 plus R sub A 112. So B sub A 2 is 112 millimeters. So there are two values for joint A. We'll start with 0 and it goes up by the amount of B sub A to 112. And then for this is joint A. At joint B, a little to the left of joint B is the end of the and at the center or R sub B, which is equal to 56 kilonewtons. So little to the right of joint B, B sub B 1 is equal to B sub A 2, and then minus the area of the triangular loading, which is downward. It causes, develops shear which is negative. So it should be a negative area of the loading. We have B sub A2, 1/2 of the loading, 42 kilonewtons per meter times 8 meters. This is B sub A2 is 112 minus minus 6 that B sub B2 is equal to B sub B1 plus the reaction power RD is 56 minus 56 plus 56 plus 0. So it closes the shear diagram, starts with 0 at the left and ends with 0 at the right. So that's one way of making us confident that the shear diagram, the shear values were computed would be right because our diagram for shear closes. It's uh, it's a closed diagram. Starts with 0 here and it goes up by the amount of parts of A, which is 112. Then this loading diagram is positively decreasing. So the slope of the negatively decreasing. The slope is negative and decreasing. So from maximum slope here, it gradually decreases and then goes to value of 56, negative 56, and then plus the reaction at RB is back to 0. So the shear diagram minus 56. Okay. Then we'll compute for the moment values. In computing for the moment values, usually at the location of 0 shear, this is where we can formulate our shear equation to determine the value of moment at that location where shear is 0. We assign that as our x. It's much simpler and easier to determine x from the right support because of the variation of the loading, since considering the magnitude of the loading here, we can assign this as our W. It will involve only regular loading, while if you consider the the left segment, it will be a combination of triangular loading and rectangular loading, meaning the computation of x using the right segment from this point is involving only few number of loadings together with the reaction in determining x. Okay, so that it reduces the risk of committing errors from the numerous or the number of forces involved in the determination of the unknown value. So when there is a point along the shear diagram, which is 0 in this case, that will also be the location of the maximum moment. Okay, 0 shear means moment is maximum. Because if you will solve for the moment somewhere at this point, it will be the area of this. We can actually compute this area, but it's much. We can simply solve for the magnitude of the moment by considering the equation that we can formulate for shear, equate that to 0, and then we can determine x. And from that x value, we can solve for the moment somewhere here by considering this segment having a triangular loading plus the reaction RCD. Okay, we do that, then we can compare with the determination of that moment from the left segment. At this particular point, we will draw a free body diagram of this the right segment and indicate the we have here the the action as a B. Shear here is 0, so B equals 0. And if we have to solve for that shear, then it will be a function of x, and we can solve for x. We actually has also a moment. So if we designate this as point C, this is B sub C. This one is M sub C. So submission forces along Y was 0 respectively. We will have B sub C upwards positive plus 56 kilonewtons and minus the load, triangular load with maximum magnitude of W. We have W times X plus 0. Since B sub C is 0, so what remains of our equation, we will solve for W here, we will express W in terms of X. So transpose this to the right, is positive, and Wx divided by 2 is equal to 56. So by ratio and proportion, because this is taken from the main beam, you can have the small triangle described by W and then X, and main beam, which is again maximum magnitude of loading of 42 on the span of 8. So we will have W is to X as 42 is to 8. So that we have W is equal to 42 divided by 8. .25 X. So that this equation for W will be substituted here. It's 5.25 X times X divided by 2 plus 56. Or we have 5.25 divided by 2, 2.625, 2.625 X squared plus 56. Therefore X square root 4.62 meters. So this X is 4.62. Therefore from the left, this is 8 minus 4.62. 3.38. moment at the right, left segment, left the support is 0, and then it goes up to a value which is maximum at point C. So moment values, seems to be 0 because again there is no shear area before point A, and the fact that a hinge will not carry any moment, so it should start with 0. And then at point C, we can just solve this the corresponding value of moment at C from this because we know already W is equivalent to, from the value of X, you can just substitute this X into the equation for W. 5.25 times 4.62. 24.25 millimeters per meter. So we have 24.255. By this magnitude of W known, then we can determine the moment at C by summation moment at joint C equal to 0. We have clockwise positive M sub C minus 1/2 times 24.255 times X 4.62. This is the area. This is the total force acting at 1/3 of X from point C. So we have times 4.62 divided by P. And this is plus. We have the same moment at point C. So this is plus and minus 56 times 4.62 is equal to 0. Or M sub C equals 56 times 4.62 minus 24.255 times 4.62 times 4.62 divided by 6. 172. Okay, we have the moment at C, 172.44. This is the moment at the right support. Moment at the position where shear is 0. So M sub is 0, M sub C is 172.44, and then the joint B, M sub B is equal to 0. But that this support will not develop any moment. So we'll just try to check this value by considering the right segment, because this value is computed using the right segment with X distance from joint B to main C. So let's solve for M sub C using the left segment after we draw the moment diagram. So we just draw the moment diagram first, because before finally checking the value of the moment at C. So at joint C, we have this moment at sea, 172.44 kilometers. And then drawing the moment diagram, this shear area is positively decreasing from maximum here at joint A to 0 at point C. So it is decreasing in positive because it is the positive side above the 0 reference line. So the slope for positive, uh, a positive slope is from lower left to upper right, and it gradually decreases from maximum here. Maximum is vertical, and then it gradually decreases to 0 at joint C. So the behavior of the moment diagram is positively decreasing. Okay. Then this area is negatively increasing, negative, and then increasing in magnitude from 0 at C to 56 at joint B. And a negative slope is from upper left to lower right. And starting from 0 at this point, it gradually decreases. So this is now the moment diagram. Maximum of 102.44 kilometers. And then from this moment diagram, we can also draw the elastic curve, which is this one. I just drawn this ahead. But the behavior is bending downward. It is opposite to the area or the behavior in the moment diagram. If the moment diagram is positive, then the elastic curve should be downward. That's the consequence of having a positive moment, all positive moment. So the elastic curve, meaning the beam will bend following this elastic curve as soon as this loading will be applied on the beam. Okay, so that's how we project the elastic curve. And the important thing again for the elastic curve is for the designer to look into the different occasions where we can make our splices or we can stop the pouring if we are using concrete for the beam. And then our reinforcements also could be spliced at the location where moment is 0, or if there is any point of inflection along the span of the beam. Okay, so this completes the analysis portion that will be used in the design. So let's now consider this moment of 172.44 in sub C computed from the left segment. So using the right segment from A to C, the loading is rectangular, trapezoidal with W at point C. Then we have 42 kilonewton meters at point A. We have the reaction here. W is 24.255 kilonewtons per meter. So at point C, this will be our moment of C. The distance is 3.38. And then we have to divide this trapezoidal loading into triangular and rectangular. And the magnitude here is the difference of 42 and 24.255. Forty-two minus 24.255. 17.745 kilonewtons per meter. So, we saw moment at joint C. Equal to 0. We have counterclockwise positive in sub C plus the moment of the triangular portion of the loading, which is the 1/2 times 17.745 kilonewtons per meter times the span of 3.38 meters. The moment arm from point C, this triangular loading is 2/3. Okay. The centroid of the triangular loading is 2/3 from the zero load for the triangle. So you have 2/3, 3.38 meters. The seriousness. Then the rectangular load is also plus 24.255 times 3.38. The moment arm from point C is 1/2. So this is times 3.38 divided by 2. It minus the moment of RA from point C. 112 times 3.38 should be equal to 0. And computing for insert C is 112 times 3.38 minus 24.255 times 3.38 squared divided by 2 minus 17.745 times 3.38 squared divided by 3. 172. Okay, this is just to check the accuracy of our computation for M sub C from considering the right segment to that of the left segment. In which we have used the left segment because it's more easier. As you can notice, you can compare the computation for M sub C using the left segment, using it on. It involves 3 forces, while in our computation for M sub C, there's only 2 forces. So one less load in developing the moment to solve for that moment is less chances of committing error. So one less of committing it. Because sometimes in our writing of the numbers, we can, without noticing it, the placement of the digits might be interchanged, if we have several numbers. So to at least minimize the writing of or using the previously computed values, then it's easier, or it's much simpler and easy in this case. Actually, this ruling could just be reversed, as shown in the example problem by Hiveler. There is a problem similar to this one, but this is being reversed. You can also do that. No? If you're given a problem like this, then you can also reverse the loading, so that it will be rising from zero at the left and then increasing, and then you can you should always use this, or if you are going to reverse this, then you will also reverse this one and solve for the moment using this triangular loading only, to at least, no, uh, minimize the number of forces that will be used in computing for moment. That's our sample for shear and bending moment.